A shift register is a group of flip-flops, usually D-type, linked together, so that the output of one becomes the input of the next on each clock pulse. Classification: based on how data enters and leaves, we have four basic types. SISO, serial in, serial out. 1 bit enters each clock, 1 bit leaves each clock. SIPO, serial in, parallel out. 1 bit enters each clock, but after n clocks the whole n bit word is available on parallel outputs. PISO, parallel in, serial out. N bits are loaded simultaneously, then 1 bit leaves each clock. PIPO, parallel in, parallel out. N bits are loaded and later read out in parallel, essentially a bank of flip-flops. Basic architecture: imagine a line of people passing a secret note to the right. In SISO, each person receives a new letter serial in and passes the note to the next serial out. In SIPO, the note is built one letter at a time, and after the line is full, each person can read their own letter parallel out. In PISO, everyone writes their own letter on a board parallel in, and then the line reads them out one by one serial out. In PIPO, everyone writes a letter and can read it back together parallel in out. All four share the same physical cells, a chain of D flip-flops, but the surrounding control logic load multiplexers enable signals output registers determines the mode. The SISO register works like a bucket brigade. On every clock edge, the data bit present in the first flip-flop is pushed to the next, and so on until the last flip-flop's output appears at the serial out pin. Operation per clock, assuming positive edge-triggered D flip-flops. At the rising edge, each flip-flop captures the value present on its D input. The D input of flip-flop I greater than 0, is connected to Q of flip-flop I-1. The D input of the first flip-flop receives the external serial in bit. Timing diagram for a 4-bit SISO. Clock low high low high low high low high. Serial in 1011 ... Q0 flip-flop 0 1011 ... Q1 flip-flop 1 unknown 101 ... Q2 flip-flop 2 unknown 10 ... Q3 output unknown 1 ... X denotes undefined before the first clock. After n clocks, the first bit injected appears at the serial out. The register thus introduces a latency of n clock cycles. The SISO is used for data serialization, shift register counters, and simple delay lines. A SIPO register converts a stream of serial bits into a parallel word. Think of it as a conveyor belt that collects individual packages, bits, and after the belt is full, loads a truck, parallel bus with all packages at once. Serial data S sub t is fed to the D input of FF0 each clock. After the kth clock, the state vector is Q sub t equals open bracket S sub t minus k plus 1, S sub t minus k plus 2 ... S sub t close bracket. Most recent bit on the leftmost flop. When a load or output enable signal is asserted, the parallel outputs P sub I equals Q sub I become visible. If S equals open brace S0, S1 ... Sn minus 1 close brace is the serial sequence. S0 first received, the parallel word after n clocks is. P equals open bracket Sn minus 1, Sn minus 2 ... S0 close bracket. MSB on the highest index output. Thus the register performs a reversal of order if the most significant bit is expected first. Example -8-bit SIPO receiving the bitstream 10110011 will present the parallel word 0B1100110 after 8 clocks, assuming MSB is output Q7. Timing: a single enable pulse after n clocks latches the parallel bus. The register can continue shifting new bits while the previous word is held, double buffered designs. A PISO register does the opposite of a SIPO. It takes a full parallel word and releases it one bit at a time. Imagine a stack of cards, parallel inputs that are turned over one by one to a reader. Functional behavior with n flip-flops. Parallel load. When the load control LD is high, the n data lines DI are routed to the D inputs of the flip-flops through a set of multiplexers. On the next clock edge, the entire word is captured simultaneously. Serial shift. After loading, the load line is deasserted. From then on, each clock pulse shifts the contents rightward, and the least significant flip-flop FF0 drives the serial out line. Timing analysis for a 4-bit PISO. Clock load high low high low high low high. Load 10000 high for 1 cycle. D3 to 0, 1011 parallel word 1011. Q after load 1011. Serial out unknown 1101. The first serial bit appears 1 clock after the load pulse. It takes n clocks to shift the entire word out. PISO registers are used in UART transmitters, DAC drivers, and for sending parallel sensor data over a single wire. Key point: the parallel load multiplexers must be fast enough to meet setup time for the next clock edge. Otherwise, a setup violation occurs. PIPO register is simply a bank of n flip-flops that can be written and read in parallel, like a small RAM cell without address lines. Load phase: when the write enable WE is asserted, the external n-bit bus D sub I is connected directly to each flip-flop's D input. On the active clock edge, every flip-flop captures its corresponding bit simultaneously. Hold phase: WE is deasserted. The stored word stays unchanged regardless of changes on the external bus. Read phase: the outputs Q sub I are continuously available on the parallel out bus. If a read enable RE is required, for example to place outputs on a shared bus, a tri-state buffer controlled by RE isolates the register. Timing diagram: 8-bit examples. Clock low high low high low high low high low high low. Write enable high low 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 high for 1 cycle. Data bus D7 to 0, 10110011 data present while write enable is high. Output Q7 to 0 after load, 10110011 visible immediately after edge. The register can be read anytime after the load edge, with no additional latency. PIPO registers are used for holding configuration words, pipeline registers, and as temporary storage in state machines. The main design consideration is race through. The combinational path from D to Q must meet the clock to Q timing. Otherwise, the data may appear too early for downstream logic. Explanation: shift registers can be described mathematically using either state space notation or Boolean equations. State space model: let the state vector x of t be the contents of n flip-flops at time t, a column vector of bits. The input u of t is the serial in bit for SISO/SIPO or the parallel word for PISO/PIPO. The next state equation for a simple write shift register is x of t plus 1 equals a times x of t plus b times u of t. A is an n by n matrix with ones on the subdiagonal. A of I comma I minus 1 equals 1 for I equals 1 to n minus 1, and zeros elsewhere. B is an n by 1 column vector with b0 equals 1. New bit enters the lowest order flip-flop, and zeros otherwise. For a parallel load, PISO/PIPO, the equation becomes x of t plus 1 equals L times d of t. L is the load selector matrix. Identity when load equals 1. Boolean expressions: for each flip-flop I, 0 equals least significant bit. The next state logic is Q sub I of t plus 1 equals if LD then D sub I else Q sub I minus 1 of t, using a multiplexer controlled by LD. When LD equals 0 shift mode, the equation reduces to Q sub I of t plus 1 equals Q sub I minus 1 of t. For the first flip-flop, I equals 0, the input is the serial bit S of t. Q0 of t plus 1 equals if LD then D0 else S of t. The output equations are simply out serial equals Q0 for SISO/PISO, and out parallel of I equals Q sub I for SIPO/PIPO. These models allow automated analysis, for example using Karnaugh maps or SAT solvers, and are the basis for synthesizing shift registers in HDL. Example: for a 4-bit SIPO, the state space matrices are A equals open bracket 0, 0, 0, 0 close bracket, open bracket 1, 0, 0, 0 close bracket, open bracket 0, 1, 0, 0 close bracket, open bracket 0, 0, 1, 0 close bracket. B equals open bracket 1, 0, 0, 0 close bracket transpose. Explanation: when designing any shift register, several practical knobs affect reliability and speed. Clock edge selection, positive edge or negative edge triggered flip-flops can be used. All flip-flops in a register must share the same edge. Mixing edges causes race conditions. In HDL, always at positive edge clock is typical. Enable/disable control. An enable, N input gates the clock or the D inputs. Gating the clock reduces power but can introduce clock skew. Gating the D with a multiplexer N(D:Q) is safer for timing. Asynchronous reset. A global reset forces all Q outputs to a known state, usually 0, instantly independent of the clock. Useful for power-up initialization. However, asynchronous resets add extra routing delay and must meet hold timing. Propagation delay. Each flip-flop has a setup time T-setup, hold time T-hold, clock-to-Q delay TCQ, and propagation through combinational logic TPD. The overall clock period T-clock must satisfy T-clock greater than or equal to TCQ max plus T-logic max plus T-setup max plus margin. For a long cascade, for example 32-bit SIPO, the cumulative delay of the internal multiplexers can dominate, so designers may pipeline the shift register or use clock skew balanced routing. Metastability. If the serial input changes close to the clock edge, the first flip-flop may become metastable. Adding a synchronizer 2 flip-flops in series before the shift chain improves reliability. Power considerations. Shifting many bits each cycle creates switching activity. Using clock enable to idle the register when not needed saves dynamic power. Technology-specific limits. In ASIC or FPGA, the maximum toggle rate of a flip-flop chain may be limited by the internal routing fabric. Designers often employ dedicated shift register resources, for example Xilinx SRL16 for long serial paths. Explanation: the physical implementation of a shift register is straightforward: a string of D flip-flops with optional multiplexers and tri-state buffers. Cascaded D flip-flops. The core is N D flip-flops connected D to Q of the previous stage. In HDL, a generate loop creates the chain. For I in 0 to N-1 generate FF(I:)DFF port map D arrow D underscore in open parenthesis I close parenthesis, comma Q arrow Q open parenthesis I close parenthesis, comma clock arrow CLK N generate. Multiplexers for load shift control. To support parallel load PISO or PIPO, and N-to-1 multiplexer feeds each D input. DI equals if LD then parallel in I else Q sub I-1 for I greater than 0. D0 equals if LD then parallel in 0 else serial in. These multiplexers can be realized with standard cells or in FPGAs with lookup tables. Tri-state buffers for shared buses. When multiple registers drive a common bus, for example PIPO, output sharing each output line is passed through a tri-state buffer controlled by a red enable signal. Bus I equals if red enable then QI else Z, where Z is high impedance. In ASICs, tri-state inside the chip is discouraged, instead a multiplexing tree is used. Special resources. Modern FPGAs provide built-in shift register primitives SRL16 and SRL32 that implement long serial chains with minimal routing. They are especially efficient for SISO and SIPO structures. Example schematic: a 4-bit PISO register. For D flip-flops FF3 to FF0. For 2-to-1 multiplexers feeding D inputs, select line equals LD parallel inputs P3 down to 0 connected to multiplexer 1 inputs. Serial input S connected to multiplexer 0 input of FF0. Serial output taken from Q0. This same skeleton with the multiplexer selection fixed to the shift path LD equals 0 yields a pure SISO. Fixing multiplexer selection to load LD equals 1 yields a parallel load shift register. Design tools can automatically insert the multiplexers and buffers based on the HDL description. Explanation: below are typical exam-style questions and how to solve them. 1. Output sequence of a 5-bit SISO. Problem: a 5-bit SISO is loaded with initial content 10101. The serial in line is held at 0. List the serial out bits for the next 7 clock cycles. Solution: the register shifts right each clock. Output sequence equals initial Q0, then the bits that move into Q0. Cycle 0, initial Q equals 10101, output equals 1. Cycle 1 Q equals 01010, output equals 0. Cycle 2 Q equals 00101 output equals 0. Cycle 3 Q equals 00010 output equals 0. Cycle 4 Q equals 00001 output equals 0. Cycle 5 Q equals 00000 output equals 0. Cycle 6 Q equals 00000 output equals 0. Cycle 7 Q equals 00000 output equals 0. Thus the output is 10000000. 2. Design an 8-bit SIPO for a UART transmitter. Requirement: convert a serial data stream at 115.2 kilobits per second into an 8-bit parallel word available every 8 clock cycles. Approach: use 8 cascaded D flip-flops, a clock enable that allows shifting only when a new bit is received, and a parallel output latch that captures the Q vector after the 8th clock. The clock period must be less than or equal to 1 divided by 115.2 kHz, approximately 8.68 microseconds. 3. Timing constraint for a 16-bit PISO. Problem: the FPGA flip-flop TCQ equals 150 picoseconds, routing TPD equals 250 picoseconds, MUX setup equals 100 picoseconds. Find the minimum safe clock period. Solution: T-min equals TCQ plus TPD plus T setup equals 150 picoseconds plus 250 picoseconds plus 100 picoseconds equals 500 picoseconds. Add a safety margin, for example 20%. Clock period greater than or equal to 600 picoseconds. 4. Data width conversion proofs. Show that a 4-bit SIPO followed by a parallel load register implements a 4-to-1 deserializer. Proof: sketch: after 4 serial clocks, the SIPO holds open bracket S3 space, S2 space, S1 space, S0 close bracket. Loading these into a 4-bit parallel register makes the word instantly available. Thus the pair converts a serial stream of 4 bits into a 4-bit parallel word. 5. Metastability analysis. Given a serial input toggling within 50 picoseconds of the clock edge, and a flip-flop mean time between failures of 1 hour, calculate required synchronizer depth. 2 stages give mean time between failures approximately 1 million hours. Thus a 2-stage synchronizer is recommended before the shift register. These examples test understanding of shifting operation, timing budgets, and practical design trade-offs. The 4 shift register families can be compared on 3 main axes. Data path: serial into serial out, serial into parallel out, parallel into serial out, parallel into parallel out. Resource count: flip-flops, N for SISO, N for SIPO, N for PISO, N for PIPO, same as others. Additional hardware, usually none, output latch optional, N-to-1 load multiplexers optional, serializer controller, load multiplexers if write enable needed, optional bus tri-state buffers. Latency: N clocks to see first bit at output, N clocks before full word available, 1 clock after load to start serial out, 0 parallel read after load edge. Typical uses: UART transmit, data serialization, delay lines, parallel data acquisition, ADC streams, DAC input preparation. UART transmit, parallel word to serial stream, LED matrix drivers, register files, pipeline registers, configuration storage. Power: low, only 1 flip-flop toggles per clock. Higher, all N flip-flops toggle each clock. Similar to SISO after load, but load pulse toggles all N flip-flops once. Scalability: easy to cascade many bits, for example 128-bit shift. Requires wide parallel bus for output, may limit length in resource-constrained designs. Design complexity: minimal, needs timing for output latch, possible clock domain crossing. FPGA primitives: shift register lookup, dedicated shift register LUTs, shift register plus parallel read ports. Overall, if the system only needs to move data bit by bit, SISO is the simplest and fastest. When a complete word is required at once, SIPO is chosen despite higher switching activity. PISO is ideal when a word originates from a parallel source, for example CPU registers, and must be sent over a single line. PIPO is essentially a small, fast RAM block and is used wherever data must be stored and retrieved without conversion. In practice, designers often mix these blocks. A sensor may produce a serial stream that a SIPO gathers. The gathered word is then loaded into a PIPO for processing. Later, a PISO serializes the processed result for transmission.